Okay, hi everyone. So it's the recess week. Oh, I hope you're watching this in the recess week for the first time at least. And so we'll be discussing tutorial which I call week 06.5 on fingerprinting. This is based on the week 6 lecture on fingerprinting. Okay, so I hope you have watched that lecture, because if not, some of these things that we will cover today will look a bit foreign to you. Okay, so if you've watched the lecture, I hope you've seen the some administrative reminders, such as in tutorial week 7, just before your midterms, it depends on your tutors and no attendance is taken. And tutorial in week 8 is cancelled. So just very quick reminders. Okay, so for today, we'll be discussing these 4 questions, right? And so the first 3 questions I imagine we'll be going through it rather fast, and the most interesting one will be the final question over here. Okay, and of course, since this is a video recording, in case it's unclear, you can always pause or slow down the video. Okay, so let's go. So first question is on this thing called communication complexity. And the question is as such. So let's say there are these 2 characters, Alice and Bob, and they are both serving stay-at-home notice in 2 separate rooms, right? And they want to communicate to each other, you know, like via SMS. But the thing is, they get charged $1 for every bit they transmit to each other. Okay, so well, let's say they want to communicate numbers. They want to communicate integers, right? Alice has an integer x and Bob has an integer y. Both are non-negative and less than 2 power n. So we want to know Bob wants to know whether x equals to y. And how we do it is that Alice will first send the number x to Bob, and then Bob will compare compare x to y. Okay, so what is the worst case cost of the communication between Alice and Bob? Okay, so how much does it cost? You know, like, because I say I get charged $1 for every bit. So by sending these 2 numbers, how much do they have to pay, in a sense? Okay, so what's the worst case communication cost? And well, here's an illustration. For example, Alice here has a number 1801 and Bob has 999. Okay, so Alice will send x equals to 1801. And what's the cost over here to send this number? All right, so going through the answer, the key fact here to note is that the number x is between 0 and 2 power n, okay, inclusive for the 0 side. And recall from a prerequisite revision that the binary to decimal representation, if you have n bits, then you can represent only up to 2 power n minus 1. Okay, and that's precisely what we have over here, because our number is bounded in this range, 0 to 2 power n minus 1. And so the cost is theta n. In fact, it's pretty precise, right? You have to cost exactly n just to send that number x. So, and how you may want to also argue about this, possibly you can say that, you know, with only n minus 1 bits, we can only represent 2 power n minus 1 integers, right? From 0 to 2 power n minus 2 minus 1. Okay, so this is in the range of, one second. This in the range of 0 to 2 power n minus 2 minus 1. Sorry, minus 1. Okay, you can only represent numbers in this range. And so we don't have enough to represent all 2 power n integers if we only have n1 minus 1 bits. Okay, so very easy warm-up question. Okay, so let's go through the second question. In the second question, right, notice how, well, we have to send n bits. Can we do a bit better? Okay, and this is the scheme that Alice uses. So Alice will first randomly choose a prime number p, okay, computes a x equals to mod p, sends both the prime number and the number to Bob, and then compares the 2 numbers together. Okay, because Bob will of course like use the prime number to do the same thing, mod it, and then compares a and b. Okay, what's the cost if they want the false positive probability to be less than 1%? Okay, so here's an illustration. So again, for example, x is 1801 and prime number is 131. Okay, so let's say we have mod it together, right? A is 98 after the modulus. Okay, so so after that, we'll send over the 2 numbers, A98 and P131. After that, Bob will do the same thing. Okay, Bob will compute the 999 and B is 82, because after modding by 131, it will get 82. Okay, So recall, well, it says that A is not equals to B, right? A is not equals to B because it received A 98 and B equals to 82. Then Bob concludes that X is not equals to Y. Okay, X and Y are the original two numbers that they start off with. But you know, like, because the problem here is that there could be a case where they are actually different numbers, but they get back the same value. Okay, so I can't think of an example offhand right now, but well, this is the false positive case, right? Because they actually have different numbers, but somehow they will output the same prime. Okay, sorry. Okay, so for example, okay, I think I thought of one here. X, very easy example. X may be like 2, 3, 2, 6, 2, and Y could have been like also maybe 1, 3, 1. They are different numbers. So X is not equals to Y, right? But by using the mod, right? By using the mod, so mod 131, we get 0, right? And it will send A equals to 0. And over here, prime still is the same. Bob will use the prime to mod this thing, 131 mod 131 to get 0. And it says that, hey, B, this is B, this is B, equals 0. And they conclude that, hey, A was also 0. So Bob believes that the original two numbers, X and Y, are the same. Okay, so what I'm showing in this example here is that if, for example, Alice and Bob actually have different numbers, but so happen that the prime that they chose makes it such that the two numbers give the same A and B, which is the number of the mod, right? The same A and B. Then Bob concludes that the two numbers are the same. Bob will say that X equals to Y, when in fact, the two numbers are actually different. And this is a false positive. Okay, so I hope that clarifies what it means to be a false positive. So the question again is like, what's the cost of sending the number and the prime? We didn't really specify because we wanted to try and decide like how big the prime should be. Naturally, we cannot let the prime be too big in terms of the number of bits. Okay, because otherwise that defeats the entire purpose. Our main purpose is to try and reduce the communication complexity. Notice how the prime here is way less compared to the number X. All right. So here's the answer. Okay, so the idea is actually really similar to the division hash from lecture. So suppose Alice chooses a prime from a range 1 to k, right? So this is the the largest a range that we set, and the prime that we choose is within this range. Okay, so for example, if we set for just now k to be 200, okay, notice k doesn't have to be prime, but it's just a range that we set, right? And we choose a prime from this range over here, and we get 131. Okay, get prime 131. So again, probability of false positive means that when X is not equals to Y, but their hashes actually equal, right? So this is exactly what I explained just now in the previous slide verbally. So false positive happens if A equals to B. And this happens when, if I let Z, right? Z is X minus Y. X is the original number. X and Y are the original numbers, and Z to be their difference. If Z equals to 0 modulo the P, sorry, I've been saying modulus, but I meant modulo P, okay? So the prime P is one of the prime factors of X minus Y, okay? So if Z equals to 0, mod P, it means that the prime, this prime over here, is one of the prime factors of this to make it divisible, okay? So when does this happen, okay? Or what's the probability of this happening? This is a claim given in lecture, so I hope you have seen this in lecture and try to understand it. I'll try to go explain a little bit more of the derivation, the answer after this. So the claim in lecture says that, you know, if you're given a number in this X and Y in this range, where the highest number is 2 power B, B is the length of the bit representation, okay, then the probability that their hashes are equal, right? The hashes are equal, or equivalently, this A equals to B over here is upper bounded by B. This is the length, right? Length of bits. So length of bits with representation times the ln k, and recall k is the number that we choose here over k. Okay, so this was all gone through in lecture, but in case I hope that clarifies a bit further in case you need further clarification. Here, right, if we apply this, recall that the number n here is because x and y are 2 power n. So in the claim here, right, it's upper bounded by 2 power b. In our question, x and y are both like upper bounded by 2 power n. So we set like b equals to n. That's why we substitute over here, right? So this is from the lecture. And what's the value of k that we should choose? Okay, again, this is very similar to whatever you have seen in lecture. So the goal is that false positive rate should be less than 1%. This is our goal. This is what the question wants. Okay, so what value of k will give you 1 over 100? That's the question we're going to ask. Okay, this is our goal. Okay, so there is an intuition given in the forum over here by Prof. Warud. Okay, so the copy of the slides will have the link to the forum post, but it's slightly different, but it's very, very similar. Okay, so here is just the goal in the lecture, or the prof was answering, was that he wants to be, there's the n factor over here. Okay, but in this question, we want to be 1 over 100 without the n factor. All right, so we choose k to be this value. Okay, so again, like same intuition as before, which I didn't go through, but it's in the post. But let's trust me for now and say that k is really 200n log 200n, and this choice of k will show that it's going to really give 1 over 100. So let's substitute. Let's do the derivation once. Okay, so we substitute 2k equals to this value. Okay, so it just goes in over here. Just goes in over here. Then afterwards, notice how we can cancel the n's, right? We can cancel the n. And then we extract out, we factor out the 1 over 200. This is this region over here, okay? And then it stays the same. The right-hand side stays the same, okay? Then afterwards, what do? We use logarithm rules to separate these two together, these two out. And the reason we want to do this is because notice how the denominator is log 200n, right? And we kind of like want to attempt to cancel this off. Okay, so we have log 200n plus log of log 200n. Okay, don't get too scared with the log. Okay, so again, we'll do cancellations because these are equal terms. Okay, then 1 plus log of 200n over log 200n. What's this over here? Okay, well, the ratio of this is less than 1 because if you try to log again, right, the number you get will be smaller. Okay, so the property is that, you know, like if you have a number x, then log of x is less than x. Okay, and of course, like it applies if you have log x is less than log x because you're applying the log again. So you take the ratio, move this down, right? Move this down, you get log x over log x is less than 1. Okay, so that follows from over here. So we upper bound it. We upper bound this by 1, and we get 2, and we cancel off the 200 with 2 over here to get 1 over 100 as required. Okay, so again, I think this is really nothing new. You should have seen this in lecture, but I thought I would offer like another, not really another, right? Like slowly go through it again in case you forgot to refresh your memory a bit. Okay, so right, so both of these numbers are upper bounded by k. Our goal was to say that, you know, like what's the communication complexity? How many bits do you need to encode these numbers? Okay, recall both these numbers are less than equals to k because of course, well, p is upper bounded by k by our choice of sampling. Okay, we sample from range 1 to k. A is because we mod it, so it has to be at most k, right? So k is this value. So in bits, right? So this is the number itself. We want to consider the bits. And the number of bits required is we just take the log of k, okay, to see how many bits to represent it. We get log of k equals to log 200n, log 200n. Okay, I didn't know how to say that, but I hope this expression is clear. So, well, if you try to do the math carefully, you separate these, you get log 200 plus log of n plus log 200n. And the most dominant term here is the log n over here. Okay, and this is the communication cost. Okay, so let's go on. So question 3, we have the 2D pattern matching, the naive version. Okay, so we have a text string t, and this actually is a 2D version compared to the 1D that we went through in lecture. So first, let's go through a naive approach, right? Let's consider a naive approach. We have a text string t, right? is an N1 by N2 size rectangle, and the pattern P is an M1 by M2 size rectangle. Okay, so remember M is just the smaller one, the pattern. Okay, and M1 and M2 are both smaller than N1 and N2 respectively. Okay, so it's safe that the pattern won't be too big. Okay, so what is the time complexity if we do like a naive check for each M1 times M2 size block in T equals P? So basically what we want to do is that you see this block over here, then you match it with the block of the same size, compare everything, see if they're the same, you know, then repeat, like shift it around and compare again. Okay, so that's the question here. What's the naive time complexity? This shouldn't be too difficult, but it will motivate for the next question. But again, like the time taken to brute force just the pattern once, right? Just this pattern once is I hope it's clear. It's really just theta of M1 times M2 because that's the size of the rectangle. But the question is, how many times do we need to brute force the pattern? Okay, if you're being careful, notice how like it is not just N2, or rather N2 is too like conservative because it will this is do it once, do it twice, do it thrice, do it 4 times, and do it 5 times. Okay, this is not N2 times. This is like, if you count like this is not N2 times. There's this here that we don't really consider. Okay, so if you look at the top left corner, right, how much can you move it vertically? So in this example, I illustrate vertically first. How many times can I move it vertically? Because this is size of M1. I hope we can see that this top left corner, right, you can only move it vertically in N1 minus M1 plus 1 position. Okay, so there's N1, take away M1. Okay, so take away M1, this is, and then add 1 to it. There's a lot of ones to say, but I hope this is clear. Okay, so this is the number of times you have to move it vertically, and horizontally, same thing, is N2 minus M2 plus 1. Okay, so this region over here, that's how many times you can move it horizontally. So therefore, you need to brute force the pattern this many times, these two expressions multiplied together. And so because each brute force takes M1, M2 time, you just multiply every single thing, right? Just multiply every single one of these things. Okay. And well, if this was like too hard for you to see, then of course you can just express it as N1, N2, M1, M2, because N1 upper bounds this value over here. Okay. All right. So yeah, so that was, I hope that was pretty simple. But really the most interesting question of the day will be this Karp-Rabin version. Okay, so this might take some time. I don't know how long I'll take to explain it, but hopefully I get to explain it clearly. Okay, so again, we want to extend the Karp-Rabin algorithm to solve the problem in O, N1, N2 time with 1% probability of false positive. Okay, assume that this holds. Okay, so numbers like the numbers might be very large, but assume that, you know, like even if it's large, it can be done in constant time. Okay, so let's see how different it is with the previous one. So previous one we had, you know, O, N1, N2, M1, M2, right? And this cost is incurred by every time we do a matching, there's always this time spent to check that every value is matching. Okay, there's this time spent, and notice how, you know, like this term vanishes away, right? So this becomes O1, becomes a constant time, meaning that an idea would be we want such that when we try to do a matching, this single match can be done in O1 time. Okay, like a very fast operation, O1 time, and maybe we'll do it then N1, N2 times, right? Do that matching N1 times N2 times. Again, because we are there's some trade-off here involved, because there's some probability of you being wrong, where in the case where they're actually different, right? So maybe X, this is Y again, same as before. When X is not equals to Y, maybe their hashes could be equal. Their hashes could be equal, and this will be a false positive. Again, this is same as before in question 2, right? So let's work through this carefully. Okay, how do you, first of all, like the question we have, right? How do you even hash a rectangular block of text? Okay, so how you can think of it, try to view it in sneaking manner. Okay, so like something like this. So it kind of snakes, okay? So view this block as a binary number. So if you have this block over here, 101, 110, view it as this binary number over here. Because normally if it's just 1D, right? For example, you have like 110100, then we just view this normally, like this is the binary number. But if it's a rectangular text, try imagine it like it snakes like that. Okay? And that's how you view this this block of text as binary number, and then we'll convert it to decimal and hash it, okay? Or conceptually convert it to decimal. So the decimal in this block is 2 power 1 plus 2 power 2 plus 2 power 3 plus 2 power 5, because like these terms are 0, right? So just ignore them. Okay. By the way, like this question, we'll just assume it's binary for now. Of course, it can be extended to generalize alphabet in a more general case, but let's just focus on binary for simplicity. Okay, so that's why the block in decimal is such. Okay, so we'll convert to decimal in hash, and this is how you hash the rectangle block of text. So before we go on to the card ribbon formally, let's recall like the rolling hash approach in card ribbon. And again, this is something you've seen in lecture, or hopefully you've seen this in lecture, but I'll just recap. So, you know, like this, for example, this is the pattern, right? The pattern in 1D case, the pattern is just maybe 3 bits. Okay, so it'll be something like 2 power 2 times D plus 2 power 1 times C plus 2 power 0 times B. This is how you view the decimal. And well, if you try to roll it right by 1, this position shift 2 power 2 times C and this. I won't say it out loud again. Okay, so this is like the representation in decimal for these two hashes. Like let's say this is the decimal for this is x1 and the decimal for that is x2. Okay, so how do I derive x2 from x1? When we do the rolling, right, how do you derive? Notice how the powers of C and powers of B, they increase by 1, right? So you can imagine, maybe you can multiply by like there's some multiplication of 2 here, but you can't multiply by 2 immediately because of this term. Okay, so what you do here is that x2 is equals to take x1, right? Take x1, subtract away 2 power 2 times D, subtract away the leftmost term, okay? Subtract away, and then you are left with this. Then you multiply by 2 to get this area, and then add back 2 power 0 times D. Okay, so hopefully you get the gist of this by now. Okay, and if you try to work out the details, notice how this is like, well, this is just expansion. Okay, so this is just expansion, and a concept given in lecture should be that division hashing is linear. So you can see it as like hx equals to, if hx is x mod p, then it's the same as h of x2, right? Is the same of h of x1. So take the h of x1, multiply by 2, like this is the term over here. Take the term hash of 2 power 3, right? Times d and hash of this, okay? And yeah, so this is what you have over here. All right. So let's go on. Okay. So we try to generalize this to the 2D case. Instead of rolling like in a 1D case, we will try to roll column by column or row by row. Okay. So from a high level, like let's imagine how the algorithm is going to look like. So we can imagine start from the top left corner, and then we'll roll by adding this column number 4 and removing the first column. Okay. And then again, we keep rolling column by column. Okay. Then again, like conceptually, you have to restart, right? You have to restart from this region so that you can roll. It's very similar to the naive approach, just that we try to imagine it in terms of rolling the hash. Okay, so you roll the hash down here vertically, okay, by removing R1 and adding R5, and then again you do the horizontal rolls. Okay, so roll column by column. So let's consider like what hashes do we need for the 2D rolling hash? Okay, because just now notice how here, right, we have to remove column 1 and add column 4. So you can imagine like, oh, you actually need the column, the hash of every column, okay, that is of length M1. So all these are needed so that, for example, if you start off, let me use another color. So like this. So you can imagine like to roll it to the next hash is by removing this and adding this, right? So that's why you need every column. And notice how every row we consider it, okay? So every row as far as we can go, right? As far as we can go vertically down, we always do an entire sweep to the right. Second of all, notice how like the only time we need to roll vertically down, right, is for the first, like when we are trying to reset, right? So we start off with this, then we reset with this. We don't really need to consider like the other ones, like these row hashes, because again, once we roll this down, right? Once we roll this down, then what you can do is you just use the column one to hash horizontally, like roll horizontally to the right. Okay. So this is what we need. And again, like, of course, we need the current hash, right? So we need the M1, M2 hash for the row currently worked on so that we can restart from left to right easily. And again, we can compute this, right? We can compute this using the vertical row hash. We can compute this by using the row hashes so that we can roll down. All right. So, well, do we need to pre-compute all? Let's see. So we can maintain N2 of such hashes at a time when going column by column. Okay. So when doing the next row, apply 1D rolling hash to all N2 of them. Okay. What I mean is that, remember just now I said that, hey, I need all these hashes, right? But do you need to pre-compute every single one of them? Like, do you need to compute like 1, 2, 3, 4, 5, 6, 7, 8 times 3, like 8 times 3 over here? What you can do, and what I'm trying to say here is that what you can do is compute the first 8 first, okay? And then you don't need to compute like naively the next like 8. You can just apply the 1D rolling hash, okay? Just do the 1D rolling hash to all N2 of them, okay? And this is fast, like this is O1, as you've seen in lecture, okay? So you don't really need to pre-compute everything, but rather just apply it as needed, okay? So let's try to flesh it out, okay? How should we hash the vertical columns? Because this is a detail I omitted. Remember, I always keep saying that we sneak, like we can imagine the binary number, the rectangular text to be like a sneaking pattern, right? So is it like 2 power 0? Like how should this be like that considered? Because the pattern could be something like that, okay? So again, so for example, right, let's say this is the pattern, right? Pattern is arranged in this way because I mentioned that we follow this sneaking pattern, right? So it's 2 power 11 down to 2 power 0. And notice how, if we take the rightmost column, right, this is kind of like the simplest, right? The simplest because it has the smallest terms, right? But notice how it is not consecutive. It is not like 2 power 1 here, it's not 2 power 2 here, it's not 2 power 3 here. But rather, they differ by steps of 3. They plus 3, plus 3, plus 3. And the plus 3 comes from the length horizontally of the pattern. Okay, so notice that first. So it also easily extends to the leftmost column. How do we do that? Is by multiplying like 2 power some appropriate power. Okay, so in this case it's 2 power 2 because the distance here is m2 minus 1, right? So we just multiply by m2 minus 1. Okay, so it's this. So fleshing it out in detail again. If we let Cij to be the column hash starting from the index ij as the topmost value, right? So for example, here this is 13. So this is C13. How do we get from C13? Or how do we compute C13, right? C13 is computed in this manner. This looks very scary. Okay, this looks very scary. But really what I'm trying to say here is really just 2 power 0 times the value here. So times the value here, times the value here, then times this value here, times this value here, okay, V1, V2, V3, V4, and then add them all up, right? This is really what this is trying to say. Okay, maybe I'll try to go through it in a bit more detail. So again, we have how many values? We have M1 minus 1 values. This is where the summation comes from, right? Oh, sorry. Let me restart that. Not M1 minus 1 values. This is M1 values. This is M1 values, and there are M1 terms here starting from 0, right? And then what's this KM2 over here? right? This KM02 over here, the K is because we want this. Notice how this is 0 times 3. This is 1 times 3. This is 2 times 3. And this is 3 times 3, right? The number 3 here comes from, as I said before, the M2, right? So this number here is the M2. And this over here is the K, because this is what's increasing. And intuitively, this is just like trying to step by the correct amount. Okay? So I hope this is clear. The times this, right? This is just a scary way of trying to index that location, like the value at that location. Okay? So, all right, so let's go on. This is how we hash a column. Okay? This is how we hash a column. So how do we roll hash by column? So we have a pattern, right? We have the pattern here, and we try to roll by putting one column in and taking one column out. And it's very similar as we have seen in the 1D version. It's just a bit more gory detail of mathematics that we have to deal here. So how do we go from h of y? Let's call this y1, right? H of y1 and call this region h of y2. How do we deal with that? So, well, again, same as before. Notice how you have to take out the leftmost value first, right? You have to take out the leftmost value first, take it out, and then notice how you have to multiply everything by 2, right? Because now this is 10. Notice how this is 10, this is 11, this is 7, this is 8. So everything here in these two columns, it'll multiply by 2, right? So that's why we multiply by 2. Okay. And after that, we simply add back what we need, which over here is the C of I, J plus 3, right? Remember this is, if for example, we start off with this is Cij, right? This is J plus 1, this is J plus 2, and this is J plus 3. Okay, so that's why we have to add Cij plus 3. Okay, so maybe I was a bit fast in this particular one, right? When I say I remove this value, remember when we say Cij, right? When I say Cij, it's actually 2 power 0, 2 power 3, 2 power 6, and 2 power 9, right? So there is a need for you to multiply this by 2 power 2 for everything. Because over here, right? Over here, it's not exactly 2 power 0, 2 power 3, 2 power 8, and 2 power 11. So you have to multiply everything by 2 power 2. Okay, so that's where the 2 power 2 comes here. Okay, so I didn't explain that in detail just now, but hopefully it's clear. All right, so follow these steps and you get the hashes. Like this is how you roll the hash from column to column. Okay, by column. Okay, like horizontally by column. Okay, so well, this is the formula that we have, right? If R is a subrectangle with the northwest corner at Ij, so this is Ij, let's say this is Ij, right? To get the hash at Ij plus 1, right? This is Ij plus 1, you just follow this formula. And this is the same thing as before, but it's just maybe a scarier way to write it, a more generalized version, where we put the M2, we put the M2 over here. Okay, but really it's really the same thing as I explained just now, just that we put in the generalized form. Okay, you can pause and try to verify that this is really the case. Okay, so we discuss like column by column. It will get repetitive if I discuss like rolling vertically down row by row. So we cannot really let's not discuss that. Okay, let's just say it can be done in similar manner. So I'll just skip that because that's gonna take too much time. But again, it can be done pretty much the same thing. So try to define like a format for the row for yourself, and then like how do you hash down, right? How do you hash down? How do you roll it down? I mean, okay. So putting everything together, a possible pseudocode might look like this. And again, like it doesn't have to be like this. You might have your own version, but here is a version that I think works. Okay, and it looks like a lot of text right now. So let's try to break it down what I'm trying to do. You may wish to skip it if you roughly know the idea already, or you can pause the video and try and see if you can come up with it yourself. So the idea here is that well, we try to hash the pattern first, right? Because every time this pattern is going to be used, right? We are going to keep reusing this pattern every time to do the matching. Okay, we try to do a match. So what we do here is that, first of all, as I said, we try to find all the column hashes and all the row hashes, all these values. Notice how for column, you don't pre-compute these things, right? You don't pre-compute the second row onwards. You just compute for the first row, corresponding to the first row. That's enough for now. Okay. So then after that, same thing here. We compute for the row, and this is to roll down. And the next lines is trying to say that, okay, let's hash the first rectangle here, the M1 by M2 rectangle in the northwest corner of the entire text. Okay. And well, we computed the row hashes just now, right? These guys over here. We computed these guys over here. So let's use it. Let's just pre-compute these things. Okay. We can store all these. It's fine. Okay. So we use the rolling row by row, like vertically, to get all these values. We just like use it so that we can easily restart later on. Okay. So this is the fourth and fifth line of the code, pseudocode. And then the final part is the loop, right? So the loop is, well, intuitively, we consider the first row first, right? The first batch of rows. And then what I do here in line 7 is I say, okay, for everything row horizontally, right? Row horizontally to the right, okay? Row horizontally to the right. And every time, right? It's not evident in pseudocode, but really I'm trying to say that every single time, try to check whether the hash of this, right? The hash of this text versus the pattern, right? So I have a pattern, I hash it, right? There's a pattern, we hash it, check if those two things match. And if there at any point in time there's a match, just return true. Okay. Of course, you can include it, like you don't have to search the entire row. You can always return true immediately when you see a match. Like this is really just pseudocode for me to express the idea well enough. Okay. So again, recall like in the beginning, we hashed this pattern over here, and that's what we are using to compare with the hash of these individual column hashes. Okay. So sorry, not column hashes, these individual rectangle hashes. Okay. The next thing we do here, right, in the next tool loop is to generate the hash of these columns. Okay. These column hashes. And the reason we can do this, right, we don't need to compute this in advance is because we can just forget about this, right? We can just forget all about these because we are done with this section of the text. We are done with that. So we just need to compute it when we need it. We just need to compute the next batch when we need it. Okay. So, well, the line 6 of the pseudocode is trying to say just like, oh, just do that for every row possible. Okay. So try everything horizontally, then restart from the next row, then go on until you can't go on anymore. Okay. So this is very similar in that sense, like the way it traverses is very similar to the naive approach. Okay. Okay. So we did all this hard work, right? What was our initial goal? Our initial goal was so that we can analyze the runtime to get a time of O n1 and 2, right? The naive one was O of n1 and 2 m1 m2. This is naive. And so we want the better one to be n1 and 2. And is it really the case that it's n1 and 2? Well, I'm just gonna leave it in the slides, and I'm not gonna go through every single one of that, but hopefully you can really see that every single one of this is really O of n1 and 2, right? And line 5, because you notice how you apply the row hashes, maybe you have to think that, oh yeah, O1, a rolling hash is actually O1, so it's actually just takes O of n1 because you apply it n1 times, right? Vertically down n1 times. Okay, so everything so far so good. And well, look at line 7, right? Line 7 and line 9 are both n2s, right? Because they are just like moving to the right. They are just moving to the right. Line 7 is just moving to the right for the entire text rectangle hash. And because comparing two numbers, right? Comparing the match is also O1. right? So we don't have to worry about that. And in fact, like this observation that the matching is O1 time is really why it's much faster now. We go down from OM1, M2 down to O1 because checking for the match now takes O1. Okay, so this is line 7 and 9. And if we consider that the loop body, right, because line 7, 8, 9, 10 is just O of N2, and the looping takes this number of, we loop this many times, which is O of N1. So the total time is O of N1 times O of N2. Okay. All right. So the next thing we have to do, right? So just now we argued that, okay, this finishes in time. But again, another goal that we want is that false positive to be less than 1%, right? We want it to be like a constant 1%. And how do we do that? Very similar to question 2, we haven't set the range of prime numbers yet, right? Because I discussed like, oh, I hash this text, but hash it with what? I hash it with the prime number that I chose, and we try to work backwards to figure out this range. Again, same as question 2. We figure out the range by trying to figure out an appropriate range so that it's actually 1%, less than 1%. And the reason we have to consider this is because every line 7 is called, it's possibly the false positive, okay? And this line is called, notice how this line is called O of N1, N2 times. So a false positive happens possibly this many number of times, right? It can happen many times, N1, N2 times to be exact. Okay, not exact, but O of N1, N2, okay? So let's recall union bound, right? Recall union bound is probability of A or B is upper bounded by probability of A plus probability of B. And intuitively, how you can view it is because, like, if say this is A and this is B, right? And this is the intersection, A or B is the entire thing, right? So this is A or B, and this is the same as probability of A. Take away A plus the probability of B, right? And then take away this intersection in the middle, right? So that's how intuitive you can view the union bound, right? So if we let EI to denote the event that the IF match returns a false positive, we have this, right? Probability of E1 all the way to N1, N2. What I'm trying to say in this slide is that, again, in line 7, right, we try to match it O N1, N2 times, and each one possibly there's a false positive. Okay, so we don't want this to be a lot. And by union bound, and union bound really simplifies a lot of calculation, okay, because we can ignore all the intersection and so on, right? It's upper bounded by probability of E1 plus E2 all the way to N1, N2, right? Ideally, this is our goal. We want it to be 1 over 100. Note that at this point, I'm not saying that this is equals to 1 over 100, although the slide might seem like that. I'm trying to present to you that this is our goal. We want it to end up like that, okay? So to do that, one way is that each single one of these terms is 1 over 100 and 1 N2. Why? Because there are N1, N2 terms, and if you multiply this by N1, N2, right, there are N1, N2 terms, right? This is gonna end up 1 over 100. So we work backwards. We work backwards and try and get this probability to be 1 over 100 and 1 N2. Okay? So when does the false positive happen? Well, again, false positive happens when actually the text, right, the rectangle is not equals, I'm trying to recall what variables I use, but anyway, like what I mean by T here, I definitely must have meant that it's the, okay, I might have made a typo here or not, I don't remember, but the idea is that, you know, the region of the rectangle and the hash, right? Wait, sorry. I'm a bit confused. Okay. So the pattern, so the pattern actually, let's say T is the pattern, right? So maybe this is P and this is P, right? So if I hash the pattern, and I compare with the hash of the rectangle and they end up equal, right? That's the event that is a false positive. Okay, so one thing to note here is that M1, this term in lecture, again, the bits it's bounded by 2 power b. Both terms are bounded by 2 power b. And we put m1, m2 over here because, again, we filled the pattern in a sneaking manner, right? In a sneaking manner. In a sneaking manner, so this is m1 times m2. Okay, so m1 times m2, and this is a number with m1 times m2 bits, and that's why this is m1 times m2, because exactly that's what the claim in lecture has. Okay, so we set k to be this very nasty looking value. Okay, this very nasty looking value, and again, the computation is very similar as per lecture. I won't go through it again because it's really just repeating the same thing in lecture, maybe a bit extended, or to some extent, this is very similar to the calculation in question 2 that I presented earlier today. Okay, so if we set k to be this value over here, we'll obtain that each probability is upper bounded by this quantity as we needed. Okay, and we just note again, like, how big is k actually? K is actually, if we look at the bit representation, it's log of k, and it's O of log n1 plus log of n2, because the biggest term of k is n1, n2, right? And well, this is fits in a constant number of machine words. Okay, constant number of machine words in the word RAM model. Okay, so while I didn't really show like this calculation, but if you try to work it out, like put 200 n1 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 n2 m1 m2 log of 200 n1 n2 m1 m2, you do the math, you should end up with this probability again. What we just showed is that for every single one, or rather what I just claimed to show, is that every single one of this is 1 over 100 n1 n2, right? And because each one of this is 1 over 100 n1 n2, and there are n1 n2 terms, multiplying this together, we get 1 over 100 as desired. Okay, so yeah, so this is the correctness analysis to show the false positive is less than 1%. Probability of false positive is less than 1%. Okay, so yeah, that concludes the video tutorial. I hope that was helpful. Maybe I'll just quickly recap like what we had to do for this question. So for this question, we do carp ribbon, right? We try to extend carp ribbon, and we do that by, you know, like try to first of all consider our scheme to hash this rectangle, right? How do I hash this rectangle? Once we have that, we consider what do we need to roll a hash, right? From this rectangle to this rectangle over here. Okay, so by this over here, then after that we do that by considering like a format for a single column hash, so that we can add a column and then remove a column. Okay, so once we have that, everything else is pretty similar as the original like carp ribbon, the single 1D carp ribbon. Okay, maybe you have to consider the how to hash row by row, like vertically as well, but that's pretty much the same idea as rolling it horizontally. Okay, and once we have that, we recall that we have to prove the running time, show that the running time is within this better bound. Okay, but the probability of false positive is still 1%, a constant. Okay, and we do that again by using the observation, the claim given in lecture, where if x and y are two different things, but hashing them gives the same value, then it's upper bounded by this quantity over here. It's already shown in lecture, so please revise that if you don't you are not aware yet. Okay, I think this might be a typo. This should be like maybe p. I think this should be p, right? I'll fix that later. Okay, so yeah, thank you very much, and that concludes the video tutorial. I hope you have a great recess week ahead, and good luck for your revision for the midterms. In case there are any further questions, feel free to email me, or you can of course also ask in the forum, because if you post in the forums, everyone will benefit because they get to see the question and the response to it as well. Okay, so thank you very much. I will stop the recording here.